Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the binary eutectic system. So this is one of the type of phase diagram where we can see the eutectic system taking an example of copper and iron. So based upon this example, we'll see what is the phase diagram of this eutectic system. So here binary means a single. So in this eutectic system, what is happening? We are taking an example of copper and iron as an example, silver, copper and silver in an example. So with this binary eutectic system, we'll draw the phase diagram and we'll see how many single phases are there and how many double phases are there. Based upon this single phase and double phase, how to identify the composition of that particular system and what is the temperature identification with the help of line diagrams. Now here, the binary eutectic system refers to a common and relatively simple phase diagram found in binary alloys. And for illustrating this an example, we are taking copper and silver as an example. So generally binary eutectic system is the material which is easily melted. Okay, the type of material which easily melts is called as eutectic system. That's why we are taking the copper and silver system as an example to illustrate this binary eutectic system. So if you see in this phase diagram, so the x-axis consists of the composition, weight percentage of silver, and y-axis refers to the temperature. So in the x-axis composition, we have the composition of copper as well as silver. So copper starts with 0 percentage, weight percentage of copper is 0 here. That means the silver should be 100%. So here the silver should be 100%. Similarly, at this point, your silver is 100, that means copper is 0. So wherever you see, the total composition of these two compositions should be 100. That means if the copper starts with 0, the silver should be 100. And if you go on to the right side, what is happening? Copper is increasing from 0 to 20, 22, 60, 80 and 100. So if it is increasing in this way, what is happening to the silver? It will decrease. It will decrease from right to left. So that is the thing we have to observe. At the x-axis, the composition refers to both the materials, the copper as well as the silver. Now, here we can find the three phases which are in single phase. Okay, so what are the single phase? Single phase refers to either it should be a liquid or solid. And what is a double phase? Means combination of both liquid as well as solid. First, we are identifying how many single phases are there here. So what are the single phases? It refers to either a liquid or a solid. Now, at this composition, we have an alpha. So this is a single phase. Beta is another single phase. And liquid is another single phase. So totally we have three single phases, 1, 2 and 3. One is the alpha, this is the alpha region. Second one is the beta region, and third one is the liquidus region. So these are the three different regions we have, and these three different regions are a single phases, whether it should be a solid or a liquid. It should not be combination. So that refers to a single phase. Now here alpha refers to the solvous liquid. So it starts at this point. Okay. So at what point means you have to see the composition, you have to draw the perpendicular line on the x-axis in order to find out what is the composition of the silver as well as the copper. So at this point you have 8%. If you drop at this section, so you have to again divide these into equal parts. So exactly you will get 8. So the 8 value we are writing here. So at 8% of copper, we are getting the liquid phase. So beyond that, again, we are having the combination of solid and liquid. So this is again coming to the double phase. But first of all, we are trying to identify how many single phases are there. So in this case, we have one single phase at this point, point B. And again, if you come to this zone, okay, that means the silver percentage. At this silver percentage, you have another liquid zone that is represented by beta. So this is one of the single phase. Now again, if you go to the upper zone of this, so you're having the liquid zone. So total 3 single phases we are trying to get. And each phase is represented by alpha. Alpha represents for a single phase, that is the solvers at this point. Similarly, beta is also representing the solidus line, and above the baseline you have another zone, that is the liquid. So total 3 single phases are there. Now if you see the composition at this point, you're having 0.8% of copper, and if you see at this point, so you're getting 91.2%. So as I said, here we are having the compositions of both silver as well as the copper. That means at this point, if you have 8% of copper, then what is the remaining percent? It should be 91% of silver. Similarly, at this point, if you have 91% of copper, 91.2% of copper, then the remaining should be 7.8% should be your silver. So like that, if you have to balance both the compositions into 100%. So like this, you are trying to identify how many single phases are there. That's why if you see this, first 3 single phase regions are found on the diagram. You have to identify how many phases are there, how many single phases are there. So here you have alpha phase, beta phase and liquid phase. So 3 single phases you are having. The other phase you observe here, you have alpha plus L here and beta plus L. So this means you have two phases and 3 single phases. So step by step will come. So how to draw this eutectic binary system for this copper and silver system. So in order to draw this figure, first we have to identify what are those single phases and double phases. First we are identifying the single phases, that is alpha zone, beta zone as well as the liquid zone. So in this case, first of all we have to take the x-axis and y-axis. So x-axis represents the composition of the copper and silver. So in this x-axis, at what point, at any point if you see, the composition should be balanced. That means it should be 100. At any point, suppose if you consider at this point, the 40%, so if it is a 40% of copper, the remaining should be 60% of silver should be there. Similarly, if you consider at this point, 80% of copper is there, then there should be 20% of silver. Like this, you have to balance the composition of both the alloys what you are taking. And coming to the y-axis, you have to take the temperature. That means at every temperature, you will have different type of zone. So if you increase the temperature, what is happening? The solid line is increasing to the liquid zone. Similarly, if you reduce the temperature, what is happening? The liquid is converting slowly into the solid formation. Like that, there is a transformation of the phases from liquid to solid or solid to liquid. Or at some stages, what is happening? There will be some combination of both the liquid as well as solid. So you have to identify, you have to differentiate these zones. That's why the differentiation of a single zone and double zone has to be done. So what is single zone? Single zone refers to either the material is in a liquid form or in a solid form. That refers to a single phase. So what is a double phase? Double phase refers to combination of both the liquid as well as the solid. So like that, you have to differentiate both these zones or both the phases with respect to temperature as well as the composition. Now, at some point, if you are getting the liquid zone, so if you want to know at what temperature you are getting the liquid zone, at what temperature, what is the composition of that zone means, what you have to do, you have to draw the perpendiculars on the x-axis. If you draw the perpendicular on the x-axis, suppose at this point, point B, if I want the composition of the silver as well as the copper, what I have to do, I have to draw the perpendicular on the x-axis. So exactly, I'll draw the perpendicular on the x-axis. So it is falling at this point. So my value, the copper value should be 8. So the same thing I have written here, 8.0. So the remaining silver should be 92%. So total it should be 100%. Like this. So if I want the composition, I'll draw the perpendicular. Similarly, in the same case, if I want at what temperature these are converting into a solid or liquid zone, what you have to do? I have to draw again a perpendicular on the y-axis so that I'll get the temperature. That means at this temperature, at some 780 degrees centigrade, I am getting the composition of 8% of copper as well as 9% of silver. So this is how you have to find out the composition as well as the temperature corresponding to the point. And also you can differentiate the phases, whether it is a single phase or double phase. Now in this example we have got 3 single phases and 2 double phases. What are those three single phases? You have alpha zone, beta zone and a liquid zone. And what is the 2 phases we are having here? Alpha plus L, that means some solid plus liquid is there. That means when any body after heating you are trying to slow down, cool down, so what is happening? The liquid is transforming to solid. So during the solidification process, at some point we have the combination of both the liquid as well as solids. So that is this stage, that is the 2-phase system where the liquid as well as solid is present. Similarly, here also you have beta plus L. So alpha is what? Alpha is nothing but the percentage composition of silver. In this case, beta is percentage composition of copper. That means you have a rich composition of silver at this point. That means at the extreme right side, you have the rich composition of silver. And if you go to the extreme left side, you have a rich composition of copper. So copper with liquid is the alpha plus L zone, and compared to extreme right, you have the rich composition of silver. So silver plus some liquid. So this is the 2-phase system what you are having. So totally you have 5 phases in this binary eutectic system. 3 single phases and 2 double phases. Now if you see the theory of this, the alpha phase is a solid rich in copper. Yes, why it is solid? Alpha zone is rich in copper means the percentage composition of copper is 100 here at this point. You have 100% of copper at the left extremity. So that's why you have higher compositions of copper. That's why it is having a rich in copper, and you have very less composition of silver at this point. So alpha phase is a solid solution which is having a higher percentage of copper, and it is having very less amount of silver. That's why the silver and the solid components are having FCC crystal structure. And coming to the beta phase, so where is the beta phase? It is extreme right to the phase diagram. So in this phase, what is happening? Beta phase solid solution is also having the FCC structure, but the copper is very less. So copper is solute here, okay, and the silver is having more rich composition. That's why pure copper and pure silver are also considered at the alpha and beta phases. If you want to have the pure copper, you can identify at the alpha phase, and if you want to have the pure silver, you can identify at the beta phase. So at this alpha phase, you'll having pure copper, and beta phase you have pure silver. Why? Because the percentage composition of silver is very high at this point. That's why you have, see here, it is 100%. That means copper is very less, it is 0%. Similarly, at this zone, if you see, copper is having 100% and silver is having very less percentage of 0%. So that's why if you want to identify rich compositions of copper and silver, you can differentiate with these alpha and beta zones. Now coming to the solubility in each of these 3 solid phases, what is happening? These 3 solid phases are very limited, and at any temperature below this BEG line. So what is the BEG line? This is your BEG line. So BEG. So this curve represents for BEG line. So at any temperature below this, okay, you have the limited concentration of silver as well as copper. Okay, below this BEG line, you have very limited composition of silver as well as copper. Why? Because you have very less composition of silver at this zone, beta zone, and similarly you have very less composition of copper at the alpha zone. So because of that, below this BEG line, so you have to mark this as a border line. So below this you have very less concentration, very limited concentration of copper as well as silver lines. Now the solubility limit for these alpha phases corresponds to the boundary line. So what is the boundary line for the alpha phase? You can see the figure. So these are the boundary lines. ABC. ABC represents the boundary line. So beyond this boundary line, again it is changing from one phase to other phase. So before this, you have a single phase. But once it crosses its boundary, what is happening? It is converting from a single phase to double phase. Okay. So from solid to, it is converting with solid plus liquid zone. So this is the boundary for this alpha zone. Similarly, if you see the boundary E, G, H, these are the boundaries for the beta phase. Again, if you cross this boundary, again this beta phase is converting into double phase with some liquid, that is beta plus liquidous line. So this is the beta plus liquid. So like that, there is some boundary for each phase. If that boundary is crossing, what is happening? That phase is converting from one phase to other phase, either from single phase to double phase or from double phase to single phase. It is being converting. So you have to identify what are the boundaries for each phases or each zone, so that you can easily identify whether it is a single phase or a double phase. Now the solubility limit for the alpha phase corresponds to the boundary. So this is the boundary of the alpha phase A, B and C. And you have to label these points with these boundary conditions. And where it is lying between alpha and alpha plus beta and alpha plus L. So the boundary of this alpha zone, the ABC, what are the ABC boundary we are drawing here? This boundary is lying between alpha, alpha plus L and alpha plus beta. So the same thing we are representing here. So this phase region, the boundary, what are the boundary we have? ABC. This ABC boundary is lying between these three phases, alpha, alpha plus beta and alpha plus L. Okay, and it is increasing with the temperature to a maximum of 8 weight percentage of silver. So how it is increasing? Slowly it is increasing. It is increasing up to the point B. So at point B, what is the weight percentage of copper? It is 92% of copper and 8% of silver. So at what temperature? If you draw this here, approximately you are getting 779 degrees centigrade. So at point B, you are getting the maximum value of the weight percentage of copper with respect to silver at point B. So you have to locate this point B, and you also identify what is the composition of this point B with respect to silver as well as the copper with respect to the temperature. So this is how you have to identify point B. And what is happening after increasing slowly? It is coming back to zero at the melting temperature of pure copper at 1085. That means slowly, see, you can increase, it is increasing and reaching the maximum point. After that, slowly it is coming down and going to the melting temperature. If you see this temperature, so you are getting 1085 degrees centigrade. So first of all, what you have to do? You have to identify the boundaries of each phase. So first we are considering the alpha phase. So what is the boundary of the alpha phase? So this is the boundary of alpha phase. So A, B, C is the boundary of the alpha phase. Now at what zones, between zones this zone is lying? So you have to identify. So this boundary is lying between alpha, alpha plus beta and alpha plus L. So these are the boundaries, okay, where the ABC boundary is lying. These are the phases in between the boundary is lying. Now you have to identify what is happening in this curve. At what point it is increasing, at what point it is decreasing. So what is happening? If you raise the temperature, so from point C, you are increasing the temperature from around some 350 degrees centigrade at this point. So slowly you are increasing the temperature. With respect to increase in the temperature, what is happening here? Slowly it is increasing. So it is increasing, it is reaching the maximum value. So what is the maximum value? How to identify the maximum value? So what you have to do? You have to drop a perpendicular on the composition line so that you will get the maximum value of copper as well as silver. So here you are getting 8% of silver. Okay, what is the corresponding temperature? It is 779 degrees centigrade. So like this you have to write. So if it is 8% of silver, the remaining should be copper of 92%. So this is the 92 percentage of silver, copper with 8% of silver. Now after increasing, what is happening at this point B? Slowly it is coming back to 0. So it is reaching to point 0 at this point A. From B to A, it is reaching to 0. Why? Because at the melting temperature, you're raising the temperature, so you're getting the melting temperature. So it is coming at point A. So at point A, you're getting 1085 as the temperature. So this is the alpha phase region, how it is being changing with respect to temperature. So at some point, it is increasing with the temperature, and after some point, after reaching the maximum limit, again it is falling down to 0 at some particular temperature. So I identify the temperature corresponding to the y-axis and note down the temperature value. So here getting at point A 1085 degrees centigrade as the temperature of that point. Now at temperature below 779. So where is the 779 line? So this is the BEG line. So BEG line is the 779 degrees centigrade, or if you want to do the Fahrenheit temperature 1434. Exactly at this point you are getting 1434. This is the Fahrenheit temperature. This is in degrees centigrade. So now at the temperature below the BEG line, that is 779 degrees centigrade, what is happening? The solubility limit is separating the two phases. So what are those two phases? Alpha and alpha plus beta. So where is alpha and alpha plus beta? So alpha and alpha plus beta phase region. So these are termed as solvus line. So what are the solvus line you are having? So this line. So wherever the line which is being separating the two phases alpha and alpha plus beta, this line is called. So this is exactly separating these two zones, alpha and alpha plus beta. So that zone is called as a solvus line. Similarly, the boundary which is separating alpha and alpha plus L, that is called solidus line. So in this curve, in this boundary of this, we have two lines. One is solvus and one is solidus line. So what is solvus line? Solvus line is nothing but the line dividing the two phases alpha and alpha plus beta is called the solvus line, and the solidus line is nothing but the phases which is dividing alpha and alpha plus L. That means alpha with some liquid is called solidus line, and alpha plus beta, two solids, represents for solidus line. So that is the difference between solvus and solidus line. So like this you have to identify. Similarly, in the same way, at this point also, at this extreme right point also, that is for the beta phase, in the same beta phase, again the beta phase is also having some boundaries. It is also having the solvus line as well as the solidus line. So all these things you have to identify. You have to plot all these solidus line, solvus line for both the copper as well as the silver on the left side as well as the right side. So in this case also, we are trying to identify as we have identified for the alpha phase. Similarly, the same thing we have to replica on the beta phase also. So first what we have done here in the alpha phase, we have tried to identify what is the boundary for the alpha phase. So this is the boundary we have identified for the alpha phase. In the same way, you have to identify the boundary for the beta phase also. So what is the boundary for the beta phase? E, G, F are the boundary phase for the beta phase. Now what is the second step we have done? We have identified the boundaries, the boundary line, where it is lying, in between what phases it is lying. So for the alpha phase, the boundary ABC is lying between alpha, alpha plus L and alpha plus beta. Similarly, for the beta phase also we have to identify where is the boundary line is lying. So the boundary line is lying between beta phase, beta plus L phase as well as alpha plus beta phase. So like this you have to differentiate between these two. After that, what is the third step we have taken? We have tried to identify what is the composition, how it is increasing with the temperature. That is the third stage, third step we are following. So how it is increasing? So with the increase in the temperature, it is also rising, will it not? So you see this curve, it is rising up to what point? At point G. So at point G, it is reaching the maximum value. So in the same case, in the alpha phase also here, it is reaching the maximum value at point B. So at point B, we are trying to note down those compositions with respect to the composition axis. Similarly, we are trying to identify what is the temperature corresponding to temperature axis. The same way, we are trying to identify what is the maximum composition at point G, that is for the beta phase. So if you drop the perpendicular on the x-axis, you can identify that is 91.2% of silver is present. The remaining will be the 8.2, 7.8 is the balance of the copper. So like that, you have to identify the composition. Now from this point G, again it is falling down to 0 from G to F with the rise in temperature. So similarly, what is happening in the alpha phase, the same thing is happening in the beta phase also. So after that, you have to identify at what temperature it is coming to 0. So somewhere around 1790 degrees centigrade, you are getting this value. Now after that, what is the fourth point we are considering? You are identifying which is solidus line and which is solvent line. So the phases which are separating the liquid and solid phases is called as a solidus line, and the phases which are separating both the solid phases is called solidus line. The same thing we are trying to identify for the beta phase also. So this is called GF is called as a solidus line, and HG is called as a solvus line. Okay, so for both the phases, alpha phase and beta phase, we have solvus lines as well as the solidus lines. So like this, you have to identify. So coming to this beta phase, both solvus and solidus lines are existing. It has to exist. Why? Because it is separating the two zones. The boundaries which are separating the two zones are called the solidus as well as solidus lines. So here also we have HG as solvus line and GF as a solidus line. And try to identify what is the composition. So at this point, you're trying to identify what is the composition. So at this point, 91.2. So what is the balance? You can get 8.8% of copper. 91.2% of silver if you have. The remaining should be 8.8% of copper. So like that, you have to identify what is the composition corresponding to the maximum limit, and after that, with rise in temperature, it is falling to 0. Okay, at this point, and you have to note down what is the temperature. So like that, for both the phases, you have to do. Now, what are the horizontal line, BG line we are taking? So this is the main line which corresponds to the division of the phases. How the phases are being converting from solidus to liquid, or liquid plus solid which is being converted to solid. So combination of different phases. Okay. So main thing we have is the BG line. So this is the maximum limit. From this above and below we have to check whether you are having a single phase or a double phase. Now the horizontal line, what are the horizontal line? BG line we are taking here. This is exactly parallel to your composition line, is it not? So this line, what are the BG line we have? This is exactly parallel to your composition line. So both are parallel to each other and extends between the maximum solubility positions. So these are being extending about the maximum solubility limits. So these are the maximum solubility limits, that is B point and G point. So these are the maximum solubility limits for the alpha phase as well as the beta phase. Now this can also be considered for the solidus line also. How we are representing the solidus line? Wherever the solidus line is dividing, is converting from alpha to alpha plus L, that is called the solidus line. And again alpha to alpha plus beta, this is called as solvus line. So for both the phases, this is again solvus and solidus. Like this, you have to identify for both the phases, you have to draw those solvus as well as solidus line, and you have to make it as equilibrium for both the phases. Now, like that, you are trying to identify how many single phases are there. Similarly, how many two phases are there in this binary eutectic system is also very, very important for us. So there are 3 two-phase regions for the copper and silver. So what are those 3 here? You have to identify how many are there. So here you can identify alpha plus L is 1, two-phase system, alpha plus beta is another two-phase system, beta plus L is another two-phase system. So how many? Total 3 two-phase systems are present in this binary eutectic system. So here we are finding total 3. So what are those? Alpha plus L, alpha plus beta, and beta plus L. Now the alpha and beta solid solution coexist for all the compositions, is not. So for all the compositions, where are the compositions you have, alpha and beta is common. Any phase, if you can see any composition at any point from 0 to 100 or 100 to 0, at any composition if you see, the alpha and beta compositions are very existing at any point of temperature. Now what is happening here? The alpha and beta phase solid solutions coexist for all compositions and temperatures. At any temperature or at any composition, you can easily identify what is alpha and what is beta. Within the alpha plus beta phase, the alpha liquid plus beta liquid phases also coexist. That means within the alpha plus beta region. So where is the alpha plus beta region? This is the alpha plus beta region. So in this alpha plus beta region, you have alpha plus liquid as well as beta plus liquid. Okay, both the combination of alloys are there at this alpha plus beta region. So here alpha plus L means one solid and one liquid. Beta plus L is also in one solid and one liquid. And coming to alpha plus beta, combination of two solids. Alpha plus beta are two solids. So here two liquid solids and one both the solids. So total you have 3. So what is happening here? One liquid plus solid. Second is also liquid plus solid. And third, you have both the solids. So both the solids represents for alpha plus beta. And one liquid and one solid represents for alpha plus L. Another liquid plus solid represents for beta plus L. So totally 3 two-phase systems are present at this. And at any phase, if you see, alpha and beta are common. You have alpha and beta are common at any composition and at any temperature. So this you have to note down. Now, if you want to identify what is the composition of the 3 two-phase systems, means again you have to use the lever rule. By using the lever rule, you have to identify what is the composition. What is the composition of this silver and iron, and corresponding temperature also you can note down using the lever rule method. So lever rule method we have discussed in the previous classes, how to identify and how to draw for the two-phase system. If it is a single phase, directly you can drop the perpendiculars on the x-axis as well as y-axis. But if it's a two-phase, then you have to go with the lever rule method. So what is the lever rule method? We have to draw a perpendicular line which should contact between the two phases. From those two phases, what is happening? Wherever the intersection point is there, from those intersection point, you have to draw the perpendiculars. And from those perpendiculars, you can easily identify what is the composition, percentage composition of the silver as well as the copper. Now, as silver is added to copper, what is happening? The temperature at which the alloy becomes totally liquid, it decreases the liquidous line. That is the line AE. So what is the line AE? So this is the line AE. This is called the liquidous line. What is happening? So since the silver is adding to copper, so we have these two compositions here. Since silver we are adding to the copper, at that temperature, what is happening? The alloy is becoming very liquid. So that's why it is falling down. So this line is called as a liquidous line. This line is represented with AE. The melting temperature of the copper is lowered by silver addition. So because of we are adding some silver into the copper, okay, the melting temperature of the copper is becoming lower. So that's why there is a fall from point A to point E. It is coming lower. The melting temperature of the copper is coming very less because of the addition of silver. So that we are representing with this AE line, and this line is called as a liquidous line. And the same is said for silver. The same way, when we are adding copper to the silver, so what is happening? It is again falling down with this line. So it is also getting to EF. So just exactly opposite, whatever the thing we are doing for the alpha phase, the same thing we have to show, we have to represent on the beta phase also. Since both are different compositions, different alloys, okay, which is having the higher rich composition of, one side is having rich composition of copper, another side is having rich composition of silver. Okay, so both are also having the same properties of converting from one phase to other phase. And again, if any alloy is adding onto that copper or a silver, what is happening? The melting temperatures are being reduced. So those reduction in the melting point because of the addition of another element into that. So what is happening? The melting temperature is falling down. So the falling down melting temperature is called as a liquidus line. So in this case, for the alpha region, what is happening? A is called the liquidus line. Similarly, for the beta phase, EF is called the liquidus line. So totally you have two liquidus lines for alpha as well as the beta phase. So one is AE, another is EF. So total two liquidus lines we are having, and these lines we have to represent. And again, these two liquidus lines are passing through the BEG line. So this is called as the isothermal. Okay, above and below of this isothermal region, we are getting the change in phases. So the same may be said for the silver also. So how we are introducing the copper into the silver, in the same way we are introducing the silver into the copper also. Is it not? Same vice versa we are doing. At one position we are adding the copper into the silver, so that the silver is getting the melting temperature is very less because of the addition of the silver into the copper. Similarly, on the other side, we are introducing copper into the silver, so that the silver temperature is getting reduced, the melting temperature is being reduction. So that's why we are showing the two curves in this manner, that is the reduction in the melting temperatures and meeting at a point E. So this is the point E where these two are meeting with each other to the BEG curve. So again, if you want to know the compositions at that point, at what composition you are getting the reduction in the melting temperature, means you have to take a note of these two connection points and again drop the perpendicular on the composition line, so that you are getting 71.9% of copper, 71.9% of copper weight percentage, and the remaining should be, it should be 28.1% of silver, like that. Totally should be 100. So like that you have to identify. And what is the temperature means? Again, simply it is already drawn at 779 degrees centigrade. You are getting this BEG curve. At that point, both the alpha and beta phases are getting lower in the melting temperatures. That you have to note down. Now, if you take an example of how to represent this phase compositions by considering lead and tin as an example. So we'll discuss how to draw the phase diagram for the Eutectic system based upon this example. Now if you see this example, determination of phase present and computation of phase compositions. So for this, they are given as for 40% weight percentage of tin and 60 weight percentage of lead alloy at 150 degrees centigrade or 300 degree Fahrenheit, what phases are present? Okay, what phases are present and what are the compositions of the phases? So the example, so in the previous example we have considered for some 70 and 30. Like that, in the same way, for this lead and tin, they have taken the 60% of lead and 40% of tin at 150 degrees centigrade. At that point, how many phases are present, whether a two phase or single phase are present, and also you have to identify what are the compositions of that phases. Suppose if it is a single phase, directly we can draw the perpendiculars along x and y axis and you can identify the composition as well as the temperature. Suppose if it is a double phase, if for that composition of 60 and 40 tin and lead at 150 degrees centigrade, if you are getting a two phase system, then again you have to go with the tie line method, and from the tie line method you have to identify what are the compositions. So we'll see what is happening, whether it is a single phase or double phase, how many phases can be identified with those compositions, we'll see. Now coming to the solution of this problem, locate this temperature composition point on the phase diagram. First, you have to draw the x and y axis. X axis represents for the compositions of the lead and tin here, and y axis represents for the temperature. Okay, so what is happening here? The location of this temperature composition point on the phase diagram, and we have to show what region is existing between these two compositions. Now we are drawing the x-axis as the composition. Here you have lead and tin. PB represents for the lead and SN represents for tin. You have the composition. So here you have both the tin as well as the lead. Here also you have both tin and lead. So if the lead is 100%, tin should be 0%. If tin is 100, lead should be 0%. So like that. So at any point if you see, it should be balanced and it should be equal to 100. Okay. So like that, if you go on increasing the lead from 100, it should reach to 0 to the right side. And similarly, if the tin is starting with 0 from the right, 100 from the right side, it has to end with the 0 on the left side. So this is the composition axis with respect to x. Now coming to the temperature, you can get some scale, and you can whether 100 degrees for each unit you can take, and here 0, 100, 200 and 300. This is the thing what we have. Now the red line, what are the red line you have that is given for us? You have here alpha phase, alpha plus L, beta plus L and liquid. So this, what are the thing we have taken from this binary eutectic system phase diagram, or what are the previous slides you have. From that we have drawn this red curve. Now from this red curve, within this red curve, you have to identify the percentage composition of lead as well as tin, 40 and 60% at 150 degrees centigrade. So here the lead tin phase diagram for a 40 weight percentage of tin and 60 weight percentage of lead at 150 degrees centigrade. That means at 150 degrees centigrade, this is the exactly 150 degrees centigrade. 150 degrees centigrade. So at exactly 150 degrees centigrade, how much compositions you have here? 40 and 60. Okay, so this is 40 weight percentage of tin and 60 weight percentage of lead. This is the point what we have. So we are drawing at 150 degrees centigrade that point B. First of all, we have to locate that point B. How we are locating that point B? So this point B is located corresponding to 150 degrees centigrade, and if you draw the perpendicular, you can identify the compositions of 40 and 60% of tin as well as lead. Now that is the first representation. So in our first question, what phases are present? First is what phases are present. So for that we are trying to show. So point B. So point B, at what phase it is lying? It is lying at alpha plus beta phase. That means at combination of both alpha and beta, the point B is lying. Suppose the same point is coming at some point here. Then what we can infer? The point, what is the point B is there? The point B is lying in a single phase. Suppose if the same point B is coming here, that is also again the same point B is lying in a single phase, since it is a complete liquid zone. Again here if it is coming a single zone, but somewhere if it is coming here beta plus L or alpha plus beta, again the point B is lying in a double phase. Like that you have to infer from this figure. Since the point B, now the point B based upon those compositions, since it is lying in the alpha plus beta region, that means the point B is lying in a two-phase region, that you have to infer from this figure. So coming to the next question, because two phases are present, since alpha plus beta region, the point B is lying in the alpha plus beta region, because two phases are present, it becomes necessary to construct an tie line. Why tie line is coming here? Any point which is lying between two phase system, then you have to use the tie line process and you have to identify the compositions. If it is a single phase, directly you can drop the perpendicular lines on the x and y axis. Simply you can draw the take the compositions. But since the point B, what is the point B we are taking here? That it is lying in its double phase. We have to draw a tie line. So this tie line, how we have to draw? This tie line has to draw like such a way that it has to intersect the 2 points. So from those 2 intersection points, you have to draw the perpendicular so that you can get the compositions. That's why, because two faces are present, it becomes necessary to construct a tie line between the alpha plus beta region at 150 degrees centigrades. So we are drawing a tie line. This is the tie line we are drawing, and this tie line has to intersect these 2 points. These are the 2 intersection points. So from those 2 intersection points, what you have to do? You have to drop a perpendicular on the compositions line. So we are dropping perpendiculars like this. So this is the C alpha, one is the alpha region, and again if you drop another perpendicular, you are getting C beta. So 2 perpendiculars you are getting. That's why the composition of alpha face correspond to the tie line intersection between the alpha plus beta. That means at this point, alpha and alpha plus beta, you are getting this intersection. And similarly, the other intersection at this point is between beta and alpha plus beta. So both the compositions you have to note at this point and at this point. So that's why you are getting the at about 11% of silver tin with 89% of lead. Okay, so that is denoted at C point. If you see the C point, these 2 points. Okay, how much you are getting? 11% of tin with 89% of lead at P point. And similarly at the beta phase, how much we are getting? 98% of tin with 2% of lead. So this is 98%, and the remaining is 11%. Okay, so like that you have to identify what are the percentages compositions of lead as well as tin. So if any diagram is given, if you want to locate the point, first of all identify what is the at what composition, at what temperature you have to locate. So after locating the point, on which zone, whether it is single zone or double zone it is lying, based upon the zone you have to identify the composition. If it is a single zone, then it is very easy for us to drop a perpendicular on x and y axis and easily identify the composition. If it is following a double zone or a 2-phase region, what you have to do? You have to draw a tie line, and this tie line has to intersect both the faces, and from those intersections you have to drop the perpendiculars and identify the composition and note down those compositions with respect to the temperature. So that is how you have to solve the questions. And coming to the references, you can go through this Introduction to Physical Metallurgy, and another book is Essential of Material Science and Engineering. The third one is Material Science and Metallurgy. Material Science and Engineering are the 4 reference books where you can identify what type of phases are present in a binary eutectic system and how to solve the representation of any point in a binary eutectic system, and how to identify the compositions with respect to temperature also. All these things you can get from these references books. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.